Here we go, video 6.5 and molecular geometries. We are going to talk shortly about the VSEPR theory, that is the valence shell electron pair repulsion theory. You have the definition there on the screen if you would like it. And also, you will be taking some time to look at the PhET application activity that allows you to manipulate these shapes and learn a little bit here about why these molecules form the shapes that they do. I'd like to watch a short video that gives the example shapes that you need to write down and put into your notes, and then we will briefly discuss about them on the next slide.
After you've mastered how to write electron dot formulas on a piece of paper, which is a flat sheet and we're kind of limited to the two-dimensional world, you have to really start thinking about how molecules really look in a three-dimensional world, because that's the world that molecules actually live in. The simplest model for modeling this type of behavior, and it actually works rather well, is called the valence shell electron pair repulsion theory. And the name's probably scarier than it actually is as far as it works. We often just call it the VSEPR theory, and then we kind of just say it all together, VSEPR theory. So you'll hear me say VSEPR theory from now on when I mean the previous. So the way it works, and the name kind of gives it away, is you take your electron dot formula and you simply count electron regions around the central atom, and you realize that each of those regions is a negatively charged region, and so it's going to repulse all the other negatively charged regions, and they're going to try to get away from each other. They can't completely get away, though, because the nucleus of the central atom is holding them in. So what they do is they try to get away from each other, but they're still held by the central atom. This leads to distinct molecular shapes. And the easiest one is two regions. If you only have one atom on one side and one on the other, and they try to get away from each other, you get a fairly linear type molecule. And so that's the first one. Two regions gives you linear shape. The bond angle is 180. Stepping up to the next one, three regions. You count the regions around the central, there's three. If three regions try to get away from each other, you basically get a nice kind of pie shape, like taking a pie and cutting it into perfect thirds. So you get a 120-degree angle all the way around for those three regions. Both of those regions are still planar. They still look just fine on a sheet of paper. It's when you get to four regions that you have to go to the third dimension. You have to go three-dimensional. And what this gets you is a shape that we call a tetrahedron or tetrahedral geometry. It's four regions around a central, all perfectly symmetric. And if you take a look and spin the molecule around and look at it, every region is equivalent. And the bond angles are now down to 109.5 degrees. That's a tetrahedral geometry. So as you can see, the bond angles are getting smaller because we're bringing in more regions. We started at 180 for linear, 120 for trigonal planar. Now we're down to 109.5 for tetrahedral. So that really sums up most of what we will use, especially in organic chemistry. Now, in addition to those, you can have expanded octets, which gets you 5 and 6 regions. So to handle those, you got to go one step further. The 5 regions is a little bit complicated, but it's really just a combination of 2 and 3. You're going to have 2 atoms linear, and then the other 3 are going to be trigonal planar perpendicular to that. When you look at the shape, you see what we call a trigonal bipyramid. We call it a bipyramid because you can look at the pyramid going up to the top atom and down to the bottom atom. Those are two little pyramids pointing in opposite directions. That's trigonal bipyramid. The last one is 6 regions. And when you get up to 6 regions, you get something that should look somewhat familiar if you've ever studied X, Y, Z coordinate planes and coordinate points. Everything's 90 degrees apart or 180. It's like the X, Y, and the Z axis of three-dimensional space. You put one atom in each space, you get 6 total. Bond angles are either 90 or they're 180. You might go, why is it octahedral when there's 6? Well, if you close up, if you take every point and make a line, you get a closed three-dimensional object with a total of 8 sides. 8-sided enclosed figure is an octahedron, and so we call it an octahedral geometry. So those are the other 2 that are part of Vesper theory. When you put all 5 of those together, you've got all 5 of what we call our electronic geometries around a central atom. And that is at the heart of Vesper theory.
Now, on page 200 in your textbook, table 5, it looks similar to this right here. You can get each shape, molecular shape, the atoms bonded to the central atom, as well as the lone pairs of electrons that you are going to find around the central atom. And we represent these in a generic formula, AB. So AB2 here could be something as CO2, or an example formula BEF2, and then it's Lewis dot structure, what it is similar to look like. I would really suggest jotting this down in your notes and even making a small note card of this to have these available. And we may want to add one other column here at the end for bond angles. Some of these bond angles are listed here. They're in your text as well, and you also will be able to view the bond angles on the PhET simulation. One final thing we want to talk about here.
An s orbital is a sphere.
One final thing that we want to talk about here is going to be sigma and pi bonds. Sigma bonds are due to a head-to-head overlap and are basically our single bonds. Pi bond is a side-to-side overlap, which is a little weaker. I'd like to watch a short video here that explains a little more in detail about the sigma and pi bonds.
An s orbital is a sphere. A p orbital is a dumbbell. And these are just shapes that describe the probability of finding an electron in that space. So in an s orbital, the electron could be anywhere in that sphere. In a p orbital, the electron could be anywhere above or below the nucleus in this nice little dumbbell shape. Now I want you to look at these 3 different types of sigma bonds and in this pi bond, and see if you can tell me where the electron overlap is in relation to the nuclei. And again, the nuclei are right here and here, there, 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 there. So let's look at these sigma bonds. Where is the overlap in the electron regions? Well, it's right here. It's shaded. So this is the overlap, and it's actually between the 2 nuclei. So if the electron region overlap of a bond is between the nuclei, then we call it a sigma bond. All single bonds are sigma bonds. Pi bonds occur when the overlap is above and below the 2 nuclei and is not directly between it. Pi bonds are weaker than sigma bonds. So you could take 2 p orbitals and have this overlap to form a pi bond. Sigma bonds can form between 2 s orbitals, an s orbital and a p orbital, or this could be a hybridized orbital. 2 sp hybridized or 2 p orbitals. However it works out, just a sigma bond occurs when the electron overlap is between the nuclei of the atoms. A single bond is a sigma bond. A double bond is a sigma bond and a pi bond. And a triple bond is a sigma bond and 2 different pi bonds. So because a pi bond is weaker than a sigma bond, a double bond is stronger than a single bond, but not twice as strong. A triple bond is stronger than a double bond, but not 3 times as strong as a single bond. So
now that we have the definition of what a sigma and a pi bond is, as well as the different molecular geometries that can occur for our molecules, let's look at an example, and these can be found on the big grid sheet that we are using to practice our molecular geometries. This is side 2, and this is the key. And we have a molecule here, NH3. Your second column is asking you what type of bond is it. Well, listed here, it's polar covalent. Remember the ways we can figure out, is it an ionic, covalent, or non-polar covalent bond? You can find the electronegativity differences, subtract them, and if it falls into the polar covalent range, greater than 0.3, less than 1.7, then that is going to be a polar covalent bond. The number of valence electrons is column 3. Well, nitrogen, it's going to be in group 5A and have 5 valence electrons. Each hydrogen has 3, so 5 plus 3 will give us 8 electrons. Draw the Lewis structure for it. This is important. All of our molecules, the first element listed is going to be the central atom. So NH3, N is the first element listed. I know nitrogen is going to be my central atom, so I'm going to draw nitrogen, bonded to 3 hydrogens, 2 lone pairs on nitrogen. The octet rule is maintained, 2, 4, 6, 8 electrons. I have a proper Lewis structure. Column 5, the bond atoms. How many atoms are bonded to our central atom? Well, in this case, 1, 2, 3 are bonded to our central atom, and that is my answer. How many lone pairs of electrons are on my central atom? 2 electrons are on my lone pair on my central atom, so I'm going to have 1 lone pair. How many electron groups, or the electron group arrangement is column 7 here. Well, what shape is this going to take? Well, here I know I have 3 and 1, and if I refer back to my table, what has 3 bonded atoms to the central atom and 1 lone pair is going to be a trigonal pyramidal. So you can take a look here, and our shape here is going to be a tetrahedral and a pyramidal there for our molecular shape, trigonal pyramidal. Sigma bonds. How many sigma bonds are on my main shape? Well, remember, sigma bonds are single bonds. 1, 2, 3 single bonds. So I'm going to have 3. How many pi bonds exist? 0. Pi bonds are going to be a double bond or a triple bond. So that's going to be 0. The bond angle, again, you can look that up in your textbook, but for a trigonal pyramidal, it's going to be 109.5. So we have 109.5 there. Is there resonance? If you're remembering, what is resonance? Resonance is when I can take my shape and I can flip it, and it's going to be the same, but it's going to have basically a double bond on a different side. There is no resonance for that. And molecular polarity. Does molecular polarity exist for this molecule? Well, it is a polar covalent bond. Nitrogen's more electronegative than the hydrogens. Yes, there is a polarity pointing towards the nitrogen as it hogs most of the electrons.